The title of my talk, as Luis foresaw, is the quantum mechanics of the very, very small, and I mean very, very small, and the very, very large, and I mean very, very large. Quantum mechanics, of course, began with the very, very small, with the atom. And its first and overwhelming success was it's hard to see these electrons circling the nucleus. Quantum mechanics' first success was explaining why the atom was stable, why the electrons didn't fall into the nucleus, why they instead formed quantum motions in orbitals around the nucleus, explained not just the stability of the atom, but the periodic table, the beginning of atomic physics, molecular physics, the fundamental understanding of chemistry, of all of macroscopic physics. The size of an atom is about 1/10 of a billionth of a meter, 1/10 of a nanometer, and the science of atoms at the atomic scale is often called nanoscience. But particle physicists have gone way beyond nanophysics. In the 20th century, we have explored the teeny nucleus here, whose size is much exaggerated at the center of all atoms. And the size of the nucleus and of nucleons, protons, neutrons that make up the nucleus is 1/1,000,000th of a nanometer, 10 to the minus 15 meters. And that exploration towards the end of the 20th century turned out to be remarkably successful, so that by now we understand in great detail what goes on inside the nucleus, indeed inside the nucleons, with a marvelous theory we call the Standard Theory. We have probed into the nucleus and found the elementary particles it is made out of. They're called quarks, up and down quarks inside both the proton and the neutron. And together with the electron and similar families of quarks and leptons, or electrons, and we have identified the basic atomic point-like constituents of all matter that has ever been seen on Earth. But even more importantly, we've understood the forces that act on these elementary electrons and quarks. Of course, the force of electromagnetism that was known already in the 19th century that holds the atom together. But in the 20th century, the two forces that act within the nucleus, within the nucleon, the strong nuclear force that binds the quarks permanently inside nucleons, and the weak nuclear force, one of whose manifestations is the transmutation of elements, radioactivity. The distances we are exploring now are distances much smaller than the nucleon. Indeed, we are trying to find structure within the quark or within the electron and probing in machines, microscopes like the Large Hadron Collider at CERN, distances down to 1/10 of a nanometer. My colleagues in condensed matter physics are very proud that they're doing nanoscience. In particle physics, we are doing nanoscience. Well, I'm going to describe a bit of the physics at this scale of a nanometer. This is the realm of quantum field theory. It is no longer possible to ignore relativistic effects that Einstein explained. we have to marry Einsteinian relativity with quantum mechanics, something that was achieved already shortly after the birth of quantum mechanics. And indeed, in the first lecture we saw the Dirac equation, which was a relativistic quantum mechanical equation. And so I will first say a word about quantum fields and quantum field theory. This is, in a sense, the basic fundamental theoretical framework for our understanding of nature. It's not just quantum mechanics, it's relativity, it's the concept of a field. Put all three together, we have quantum field theory, and that is what we truly know, what has truly been tested, what truly works. But in order to explain the nature of the forces of nature, electromagnetism and the nuclear forces that act inside the atom and the nucleus, we're going to have to discuss a bit the strange properties of the vacuum, the quantum vacuum. And I will show you how it's the strange properties of the quantum vacuum that give rise to the texture of the nature, the difference between these three forces that act within the atom and the nuclei. And then I will discuss a speculation about some totally new quantum dimension of nature that many of us speculate will be discovered any week now at the LHC. And that is quantum dimensions of space and time. I'll explain what that means later. So, and then if I have time, I will say a word about the very, very, very small, much smaller than a nanometer, where string theory comes in and quantum gravity becomes essential. And I'll also say a word about the very, very, very large, the largest scales we know of and can observe, galaxies, the universe as a whole, and its fate. And all of that will be, all of our ideas about the very, very small, very, very large are based on peculiar quantum mechanical effects. Now, fields indeed were introduced in the 19th century by Faraday and Maxwell to describe electromagnetism, and you all have seen with your own eyes fields such as the magnetic field of a bar magnet. And you can actually feel the fields. Try to bring two magnets together, you can feel the force lines pushing them apart. That's what gave Faraday the intuition to come up with the concept of this field of force, magnetic, electric, that pervades space. And these fields that pervade space can fluctuate. They can oscillate. There can be waves of the electromagnetic field. And Maxwell discovered, using the equations he set down to describe the electric and the unified electric and magnetic fields, that the oscillations of these fields traveled with a speed that he could calculate. And he did the calculation. And it came out that it was equal. Speed of propagation of the electromagnetic waves was equal to the then measured speed of light. As a theorist, I cannot imagine a more wonderful moment in the history of science. You do this calculation and you discover that light is nothing but fluctuating electromagnetic fields, fluctuating electricity and magnetism. And that's, of course, how light was understood after Maxwell for many years, until the quantum revolution, in which Planck and then Einstein started by realizing that in certain circumstances there's a much better description of light as quantum particles. That when you reduce the intensity of the light, and increase the frequency or decrease the wavelength, it is better to describe light as quanta, discrete packets of energy inversely proportional to the wavelength of the light. This relation, by the way, and you notice here two constants of nature, the velocity of light and Planck's constant that Planck discovered. Now, Planck's constant not being zero means that for a given wavelength, the energy, the minimal amount of energy you can get with one quanta is bounded from below. It cannot be smaller. That's why the LHC is high energy physics. That's why it costs so much to explore short distances. Because to explore very short distances, you need a very good microscope with a very small wavelength. The wavelength is in the denominator. You make it smaller, you make the energy bigger, and that costs money. CERN uses, what, 1/3 of the electrical power of France or something like that. Very expensive. It's all because of this relationship. It's a pity that to explore the very, very small, you need these enormous energy machines. So the quanta of light behave as particles, as Einstein discovered, and we call them photons. And they are good examples of the bosons that have been much discussed in the last 2 days. Photons are bosons and elementary particles. And bosons have this property that Wolfgang referred to in his talk yesterday of being identical particles. If you have two bosons, two atoms that are bosons, or two quanta of light, of course it's hard to stop two quanta of light and put them at a given place. They always move with the speed of light. So let's take two atoms that are bosons. They're totally identical. Again, this is a quantum mechanical effect. Classical physics, it was hard to understand why two things could be identical. After all, if you look very carefully with a microscope, you'll see slight differences between them, perhaps. But in quantum mechanics, because of the discreteness of our description of nature, the lowest, the simplest components of nature, the elementary particles, can be indistinguishable. No way of telling the difference. Now, we describe such things by fields or wave functions, functions of both x1 and x2, the positions of the two particles. Now, I just interchanged them. I did that maybe too fast, so let's do it again. I have a description of these two bosons. Now I interchange them. Nothing has changed. They look the same. So our description must not change. And bosons, described by a wave function or a field, doesn't change if you interchange the position of these two particles, two bosons. It's that fact that leads to statistical properties called Bose-Einstein statistics, the fact that bosons like to congregate together. They sort of have an extra attraction. Because of that, you can bring lots of bosons on top of each other and form macroscopic fields that you see, those electromagnetic fields that you see at large distances are lots and lots of photons in the same state. Bose-Einstein condensates, which we heard about at great length yesterday and the day before, superfluids are bosons that are in the same state. Bosons like to be in the same state. But it turns out, we discovered in the beginning of the quantum revolution that there's another kind of particle which has no classical analog. And it's called fermions after Enrico Fermi and Paul Dirac, that obey Fermi-Dirac statistics. They're also indistinguishable. For example, the electron is such an indistinguishable elementary particle. Actually, an electron has a little spin, so it could be spinning up and spinning down. But one spinning up electron is indistinguishable from any other spinning up electron. And if you interchange them, you get exactly the same situation. So our description can't change, right? It's the same situation. However, in the case of fermions, when you take the wave function that describes two fermions and interchange the positions of these identical particles, you don't get the same wave function. You get minus the same wave function. But I said it's the same situation, so how come you get a minus? Well, the minus doesn't matter for some things. For example, probabilities are proportional to the square of the wave function, and it's, as you know, -1 times -1 is +1. So the minus sign doesn't matter. But it does matter in some other places. For example, you ask, what is the wave function of two electrons being at the same place? X. So that's psi of x and x. Now interchange the x's. You get a minus sign. So it's equal to minus psi of x and x. But again, it's elementary arithmetic to notice that any number that's equal to its negative must be 0. So the probability of the two electrons being at the same place, in the same state, is 0. And that is the famous Pauli exclusion principle, first enunciated by Pauli, a Swiss physicist who worked in Zurich. Fermions don't like to be at the same place, in the same state. They sort of repel. Much of the structure of the world is a consequence of the simple fact that electrons repel, are fermions. For example, atoms would be pretty boring if electrons were bosons. Every time you would add a boson, another electron, to create a bigger atom for a bigger nucleus, the bosons would be in the same state. Fermions, on the other hand, can't occupy the same state, so they occupy ever-increasing shells, giving rise to the marvelous periodic table of chemistry and all of atomic and molecular physics. It would be a pretty boring world, and even worse, I'll come to, if if electrons were bosons. Another property is that you can't construct a macroscopic field of fermions. Have you ever seen an electron field like you've seen magnetic and electric fields? Impossible, because to construct such a field, you'd have to have lots and lots of fermions in the same state. Impossible. There's no such thing as a classical fermion macroscopic field. And as I said, matter is stable. The electrons have to be in different orbits and fill out this marvelous periodic table. Oops. And finally, and perhaps most important, the stability of matter. If electrons were bosons, then it seems to be the case, although the proofs aren't as rigorous as the opposite proofs are, that matter, ordinary matter, atoms, would be unstable. All these bosons, electrons, and nuclei would coalesce and want to congregate and fall into this incredibly, in some sense, boring Bose-Einstein condensate. Ordinary matter would not be stable. On the other hand, because they are fermions, when you try to bring two atoms together, the electron clouds overlap, the fermions repel, and they repel. That's a good part of the reason why I can't stick my hand through the table. My hand is actually made out of mostly vacuum. If you look at my hand, it's made out of atoms. The atoms are mostly empty. There should be no problem to stick my hand through the table, except for the fact that these fermion clouds of electrons have this repulsion. Okay, that's all I'm going to say about quantum fields. They all play a role in the standard model of elementary particles, where we have, over the 20th century, discovered a whole bunch of elementary quarks and leptons. Inside the nuclei, we have up and down quarks. The electrons surround the nucleus to form the atom. The neutrinos are very light particles that are produced in nuclear reactions and hard to see. They're neutral. And there are two other families, exactly similar patterns of quarks and leptons, which are much heavier and radioactive. They decay to these lighter quarks and leptons. All of those particles are associated with a quantum field. And they're all fermions, just like the quarks and electrons. The other part of the standard model are the quanta of the forces of nature. The photon, which is the quanta of electromagnetism. One of the colors doesn't come out of this display. The photon, which is the quantum particle associated with electromagnetic field, and then the fields that are responsible for the nuclear forces are very similar in nature. At a deep level, they're exactly the same as electromagnetism, and they have associated quanta. We call them gluons, which are the quanta of the strong nuclear force that bind the quarks together, and the W and Z bosons that are the quanta of the weak nuclear force, and were discovered or confirmed here for the first time at CERN. These quanta of force are bosons, and they're described by bosonic fields like the electric and magnetic field, the corresponding fields of the strong and weak interactions. Well, I'll say a bit about why these forces appear so different in nature. At the heart of the matter, they're almost the same. But to do that, I will have to digress. Before I do so, I want to just say that this framework, with these particles and their measured masses, which we can't yet calculate, we don't have really a theory to calculate them, and the measured strength of the forces of these these three forces, we can just about explain, we believe, everything in this meaningless reductionist sense. We don't actually often try to sit down and calculate everything, but there is almost nothing we know in the laboratory that cannot be explained by this standard model. All the way from the smallest possible length we can imagine, the so-called Planck length of 10 to the minus 35 meters, to the edge of the universe, which is 10 to the 26 meters, 60 orders of magnitude. This achievement of physics over the millennium that it took to come up with this is one of the, in my opinion, the greatest achievements of science. We have a theory which is extraordinarily well tested in hundreds and hundreds of experiments with accuracies, sometimes approaching a part in a billion or more, sometimes in the case of these newer and stronger forces to 1 part in 10,000, 1 part in 100, and we see no deviations. Now, why are these forces so different? A large reason they're different has to do with the strange quantum properties of the vacuum. Now, I like to tell my lay friends that in doing particle physics and trying to understand fundamental forces of nature, the most important thing is to understand the vacuum. We spend most of our time studying nothing. If you understand the vacuum, the rest is trivial. Particles are, in a sense, just small quantum fluctuations in a vacuum that you have to understand. In the medium, the quantum medium that we think of when we think of the vacuum. Now, you might be surprised about that because most people's picture of the vacuum is that. This room is very interesting. All these interesting people here. Take everyone out of the room, and the chairs and the air, all matter. Cool the room down to absolute zero, even though that's impossible. What would you be left with? The vacuum. And that's most people's picture of the vacuum. Pretty boring, but classically correct. The classical vacuum is this lowest energy, homogeneous, symmetric, empty state. Nothing much you can say about it. But in quantum mechanics, that's never the case. Nothing is ever really at rest. Nothing is really ever still or boring. Now, there are many ways of explaining this, but I'm going to go back to Heisenberg, and consider a pendulum. So this is a classical pendulum. Now, the pendulum is oscillating back and forth. It has energy. If I cool it to absolute zero, so I stop it, it's at rest. This is 1 degree of freedom, just one dynamical variable, one thing that's moving. This is the analog of the vacuum. Now, Heisenberg taught us that, well, quantum mechanics teaches us that this is the wrong picture. But Heisenberg explained it nicely by saying, if you try to imagine that the pendulum is truly at rest, how would you check that? Well, you would shine some light and see, observe whether it's true. So I'm shining a laser light on the pendulum. But light consists of these little quanta of energy, little particles. And for me to see the pendulum, these particles have to bounce off it and hit my eye. And every time they bounce, they give the pendulum a little kick and set it in motion. So using the quantum nature of photons, Heisenberg could argue that it must be the case that the pendulum has a little motion. From that, he deduced his uncertainty principle. This can't be at rest according to the uncertainty principle, because then we would know where it is and what its momentum, its velocity is. And that's impossible. There's always uncertainty. It's always moving. We call that zero-point motion. Motion in the ground state, in the lowest energy state, in the vacuum. So it's very hard to see what's going on in the vacuum with our eyes, which are big and are sensitive to big wavelengths, so that we average out over all the interesting stuff going on in the vacuum and we don't notice it. So I'll show you a theorist's picture of the vacuum as calculated in one of my favorite theories, quantum chromodynamics, that describes the nuclear force as a consequence of chromodynamic fields like electromagnetic fields, but more rich. This is a calculation done using quantum chromodynamics, which works on computers, and this is an illustration of the fields, the strength of the fields fluctuating in the ground state at 0 temperature of the quantum chromodynamics. The scale here is about the size of 4 protons. So this is nuclear scale. That's why you don't see this when you look at the vacuum, because you average this out with your eyes that can only see distances 1,000,000 times larger. This is a complicated medium with very interesting dynamics that can do all sorts of wonderful things. And it's the properties of this quantum vacuum that are responsible for the structure of the difference between the 3 forces that act within the atom. The vacuum also has something we call virtual pairs. Because of relativity, every particle has an antiparticle in the universe as well. It must have, because of the principle of relativity combined with quantum mechanics. So out of the vacuum, a particle and an antiparticle can pop and then annihilate over very short times. And the quantum vacuum always has those particles popping in and out. Now, how does that affect the structure of the Standard Model? Well, the Standard Model has these 3 forces, 1, 2, 3. Where's 3? Oh, no. And they turn out at the bottom, in essence, to be the same force. The same principle gives rise to electromagnetism, to radioactivity, and to the strong nuclear force. The only difference between these forces that arise because we have these fields that couple to, say, electric charge, is that in the case of electricity, we have one kind of charge, which you all know, the electric charge. You've actually felt it, right? Static electricity. The weak force is the same kind of force, same kind of field. Only difference is that there are 2 charges. And the strong nuclear force that binds quarks together is the same kind of force. The only difference is that there are 3 charges. So 1, 2, 3. Now, the simplest and oldest and easiest and most boring is electromagnetism. There's one kind of charge, the electric charge. An electron, here's an electron with negative, Franklin decided it was negative electric charge, and here's the anti-electron, the positron, the same mass, opposite charge, positive. And as you know, 2 charges, 2 different charges, opposite charges, attract each other. They set up an electromagnetic field, which mediates the force. Here are the force lines given by Coulomb's law. They attract. We have another description, remember, of electromagnetism. The electromagnetic field is really particles. So we have another way of describing this in relativistic quantum field theory. We say the force is mediated by the photon. The photon is sort of zipping back and forth between the electron and positron, creating the force that pulls them together. This force is well known to you. It is the inverse square law, Coulomb's law. It falls off like 1 over d squared, 1 over distance squared, and vanishes as you pull the 2 charged particles apart. If they get far enough apart, the force is very small. That's why you can pull electrons out of the atom and use them to conduct electricity and run motors and do all sorts of nice things. There are quantum effects. This so far is classical. This was known to Coulomb and Maxwell. There are quantum effects. The fact that the vacuum that these charges are in is complicated, has fluctuating fields and virtual particle-antiparticle pairs, does slightly change this force law. But the effects are very small. And it takes very ingenious experimenters and a lot of work to see these effects. They're marvelous tests of relativistic quantum field theory, but they don't change the nature of electromagnetism. At least until you get here to very short distances, where something seems to go to infinity, which is always a problem. The weak nuclear force, however, is totally different. But in essence, it's the same. It arises from the same basic principles, the only difference being that there are two charges. There are two kinds of quarks and two kinds of leptons. We call them the up quark and the down quark, or the electron and the neutrino. There's also an anti-up quark and an anti-down quark and an anti-positron, the electron, and an anti-neutrino. Every particle has an antiparticle with the opposite charge, but they're two different charges. The force is mediated by a field that couples to these charges. But now it has a new property because there are two kinds of charge. And now I'm going to use the particle language. The quanta of the force are W and Z mesons. And a up quark can now do something new. It can emit a W meson and change into a down quark. The W meson can then decay into a positron and a neutrino. Now, the up quark is always confined inside the proton. So what happens when an up quark emits a W and turns into a down quark is that a proton turns into a neutron emitting a positron and a neutrino. This is radioactivity. When this happens in an atom, the charge of the atom decreases by -1, and you have transmutation of the elements, as people, the alchemists, always dreamed of. That's one difference. The weak nuclear force is different than electromagnetism. Another is the fact that the W and Z bosons that mediate the force are not massless. They don't travel with the speed of light. And also, as it turns out, the quarks and the electron and the neutrino and all the fermions, all the constituents of matter, are also massive. And in the theory of the weak nuclear force, that's a bit bizarre as well, since those particles should be massless. They should travel with the speed of light. And they would if the vacuum were the boring vacuum, but they don't. We learned how to explain this by copying the phenomena that was discussed in the last two lectures almost in exact detail, by saying that there is a Bose-Einstein condensate pervading the vacuum. Now, you can create Bose-Einstein condensates in the laboratory, and superconductors, in a sense, are Bose-Einstein condensates of electron pairs. But according to our understanding of the weak nuclear force, the whole vacuum everywhere in the universe is filled with a condensate, a Bose-Einstein condensate. And to describe it, we could say, well, maybe it's quark pairs that condense, like superconductors. But the simplest explanation is that there's a new field of bosons, a new set of bosons in nature, which are called Higgs bosons. And they condense. And the vacuum is actually filled with a Higgs condensate. Now, it turns out, and I don't have time to explain this part of it, and that in such a condensate, an electron or a W or a Z gets slowed down. It rattles around, bouncing off the particles that make up the condensate, and you end up with massive quarks and massive W's and Z's. The force is no longer mediated by a massless boson that travels with the speed of light, but a very heavy boson that weighs almost as much as a lead nucleus, and that gives rise to a very short-range force that only acts within the nucleus, and that's the weak nuclear force. Now, this model of the condensate hasn't totally been tested, because in its simplest version, it predicts a massive Higgs particle, the telltale clue that this simple story is correct, which has not yet been observed. And one of the reasons for building the LHC was to find it, and I have no doubt they will in the next 5 years. What about the strong nuclear force? Well, we've done 1, we've done 2, now it's time for 3. Strong nuclear force has 3 charges. So an up quark comes in what we call, whimsically, colors. Those are just labels of these 3 charges. We call them red, white, and blue, or red, green, and blue. Up, down quark has 3 charges. We've discovered 6 kinds of quarks, flavors, we call them. Charm, strange, bottom, top. They all come with 3 charges, 3 colors. And the chromodynamic field that couples, like the electromagnetic field couples to electric charge, the field that mediates the strong nuclear force couples to color. We call it the chromodynamic field, therefore. And in the normal vacuum, if the vacuum was just empty and boring, we would get the standard 1 over r squared law, and we would be able easily to extract the quarks from the nucleon just as we extract electrons from the atom. And if that was the case, it would be very interesting. But it isn't the case. No one has ever seen a quark. For a long time, this was one of the great mysteries. It looked like protons were made out of quarks, but you couldn't pull them out of the proton. And essentially, what we discovered was that in this theory, like electromagnetism, but with 3 charges, the vacuum, what happened to the vacuum? I have the vacuum on my computer. Can you see the vacuum? What's going on? Did you see the vacuum fluctuating before? No? The vacuum is there. Where is the vacuum? There, no. Is something wrong with the projector? I have a picture on my screen that is not being projected. Can you reduce the lights? It is very strange. Well, what you have to imagine, remember that picture, I hope that came up, of a of the vacuum being full of fluctuating fields. Well, imagine that instead of this black vacuum, there's a complicated medium of fluctuating fields. Turns out that that vacuum squeezes these force lines to form a tube of chromodynamic flux. And consequently, the force between the quarks doesn't go to zero at large distances. At short distances, it is also modified by this logarithm, which really tells us that the coefficient of 1 over distance squared, the charge of the quarks, is vanishing as you go to short distances. That phenomena is asymptotic freedom. It really means that the force, the charge of the quarks, vanishes as you approach zero distance, which is very nice for theorists, because it's very easy to calculate things when the forces are very weak. So we can calculate all the properties of quarks very short distances. But it also says that at very large distances, the force doesn't vanish, but approaches a constant. And that's why quarks are confined, why you can't pull them out of the proton, because the force just continues to be there. You have to do an infinite amount of work to really pull them out of the nucleus. That's why they're confined. This is actually a picture. Well, so this phenomena indeed led us to the theory. This theory of three charges with a force that is like electromagnetism, called quantum chromodynamics. And it really works. In this theory, we can actually see what happens when you try to pull two quarks apart. Again, it's hard to see what happens these microscopic distances with the eye, but the theory allows us to calculate. And when you pull a quark and an antiquark apart, you see that the force lines are squeezed to form a tube. And that leads to a constant force, which makes it impossible to separate the quark and the antiquark. Now, as Wolfgang said, when you go to Stockholm, which we did for this discovery and the theory, quantum chromodynamics, you get to sit with the Queen and have a nice dinner, but perhaps the most loveliest part of the whole thing is receiving this very special picture that an artist draws for each laureate. And in my drawing, you see these three quarks bound within a proton, unable to escape because of the strange properties of the quantum vacuum that prevent them from getting out. And here again is a real calculation in quantum chromodynamics done with massive computers, lattice quantum chromodynamics, not by me, but by dozens of colleagues who've been calculating away for years and years. This is a visualization of what happens when you try to pull the quarks out of the proton. This flux squeezes to these tubes, and you just cannot do it. This phenomena this phenomena allows us to do, at short distances, when the quarks are close together, just about any calculation imaginable, and therefore to test this theory with great precision. But the thing that I enjoy the most as a theorist is not so much making predictions and having them tested, but what I really enjoy the most and it took many, many years of many colleagues working very hard, was to actually calculate the masses of the proton, the neutron, and all these other strongly interacting particles that one can produce at accelerators, dozens and dozens. By now, the calculations are precise enough that one can calculate the low-line masses, like the proton, the neutron, and so on, to 1% accuracy. It's amazing. And as Louis said, that mass does not come from the masses of the up and down quarks. It comes from this confinement. The proton is nothing but a bag held together by this force that never stops. And it's a bag of almost massless quarks zooming around with almost the velocity of light, and gluons that are holding them together that are also massless and held and confined in the same way. It's just a bag of energy. And remember, E equals mc squared. So energy, the total energy of a particle at rest, is what we call mass. So all of you indeed are made out of confined energy. And the fact that we can calculate your confined energy or your mass to 1% is immensely satisfying to a theorist. This phenomenon of asymptotic freedom also helps us imagine now that we have three forces, all of which are exactly the same kind of force and only differing in the fact that there's 1, 2, or 3 charges, that they might be unified. The strong force is very strong, but it gets weaker, so it might look like the other forces if we could probe to short distances or high energies. The other forces, remarkably, the weak force also decreases, the electromagnetic force increases, gets stronger at short distances. Present-day observation allows us to track these in complete agreement with the theory, and therefore we can extrapolate as theorists way beyond present-day observation. We're not bound by experiment. If we make predictions, the experiment does not confirm them, well, then we're in trouble. But we can extrapolate. Oops. And when we extrapolate, we find these forces come together at an extraordinarily high energy. In fact, it's the energy where gravity becomes a strong force as well. Now, that's the realm of string theory, which I'm not going to say more than a word about. We have a very strong clue from what we understand and extrapolate, from gravity, which we also understand, at least classically, that all the forces unify at an energy scale which is enormously high, at a distance scale of 10 to the minus 33 centimeters, a scale that Max Planck, who knew about gravity and his Planck's constant, predicted over 100 years ago. It's called the Planck scale. And because this extrapolation suggests that unification includes gravity, we're led to incorporate gravity into our quantum field theory, and that has led many of us to a new kind of theory called string theory. We're led to that because gravity is kind of strange, very different than the other forces. Einstein taught us that gravity is a consequence of the fact that matter curves space and time. So that particles feel gravity like a light ray passing near the sun. What they're really doing is traveling in a straight line, a geodesic, in a curved space, curved by the presence of the sun. That's how general relativity was first tested experimentally. The curvature of space and time is how gravity arises. But remember, if anything is dynamical in quantum mechanics, it fluctuates. So if space and time is dynamical, space and time are fluctuating. Now, the fluctuations of space and time are pretty small. Gravity is very weak at large distances. But at short distances, it becomes strong, and the fluctuations become strong. And if we were to try to visualize space-time in a simple way, we would have pictures like this of, people call it space-time foam. We rapidly lose any confidence in our description of quantum Einsteinian relativity. That's why we've been led to superstring theory, which does a lot better in describing quantum gravity without the problems of Einstein's theory. But it, of course, reduces, as all better theories must, to the previous theory at large distances. But at distances of this fundamental Planckian length, string theory suggests that perhaps a better picture of particles is not point-like objects, but extended vibrating strings, quantum mechanically, of course. Well, I don't really want time to describe string theory or the strange quantum effects of space and time that we've been led to, where we begin to question the actual nature of our picture of space and time and wonder whether that is not just an emergent concept, and wonder what are the quanta, what is space-time truly made of. Instead, let me come back to much larger distances that will be probed at the LHC at 1 trillion electron volts, and a new quantum symmetry of nature that some of us expect might be discovered at the LHC. It's called supersymmetry. And I want to explain this new symmetry of nature that might exist as we explain many symmetries of space and time. For example, you know that the laws of physics are rotationally invariant. That means if I do an experiment in my laboratory, I drop this, I measure how long it takes to drop. Now I rotate my laboratory 90 degrees, I do exactly the same experiment, I get the same result, right? The laws of physics are rotationally invariant. They're also translationally invariant. Otherwise, it would be pretty difficult for an experimenter. They would have to write on their paper, my laboratory was located in Paris. I did the experiment at 12 a.m. My laboratory was pointing north-northeast, and I got this result. You don't have to say all of that because the laws of physics don't change when you translate in space or time or rotate. Those are symmetries of the laws of physics, rotations of space-time. So supersymmetry is a very simple concept. It's simply the fact that the laws of physics are invariant under rotations of superspace. So you got it? Of course, I didn't tell you what superspace was. So what is superspace? Space and time are perhaps the most fundamental concepts we have in physics. We describe the motion of particles in space as time progresses. We describe physics by wave functions, which are functions of space and time, fields. And there's the usual x, y, z, and time. Now imagine we have new dimensions. Oh, and the symmetries of space-time are rotations of space-time. Now imagine we have new dimensions, which I label theta. Well, you've heard of extra dimensions, new dimensions. String theorists are sort of led to think of extra x's and y's. These new dimensions I'm talking about are not those new extra dimensions. They are different. They are measured not with ordinary numbers, 1, 2 centimeters, 17.5 centimeters. They are measured with anti-commuting numbers. Numbers, theta 1 and theta 2, whose multiplication depends on the order. Theta 1 times theta 2 is minus theta 2 times theta 1. I interchange the numbers, I get a minus sign, just like fermions. These are sort of quantum dimensions. There is an exclusion principle. Theta times theta is minus theta squared, therefore is 0. Now, mathematicians invent all sorts of crazy numbers, like square root of -1. a number you square and you get -1. These numbers are no more crazy, and you can invent such numbers and multiply them and add them on to ordinary space-time dimensions, and you get a beautiful, elegant mathematical generalization of space-time and the symmetries of space-time, where you can rotate one of these new dimensions into one of the old dimensions. And just about every quantum field theory we know, or by the way, all classical field theory, can be put into superspace in such a way that the laws of physics are invariant not just under rotations of space-time, but of super space-time. That fact was discovered in exploration of string theory, actually, originally, and then quantum field theory as a kind of mathematical playing around that theorists often do. Of course, then we ask, could it apply to the real world? These ordinary dimensions with ordinary numbers, commutative multiplication, are sort of like bosons. These dimensions are like fermions. You get a minus sign, you can't have, in fact, it turns out if you try to move along this dimension, you can't move very far because of this fact. You could just move an infinitesimal amount. That's why you don't see these dimensions. Just like you can't see a fermion field. But they could be there. It turns out that in every theory we have, we can embed it in superspace, but there's a price or an advantage. It is that when you do this rotation of an ordinary bosonic-like dimension into a new fermionic-like dimension, for every particle you had, there's a new particle with opposite statistics. If you had a boson, you get a fermion. If you had a fermion, you get a new boson. So we say that we know about quarks and electrons and photons. There must be, if the world is supersymmetric, if the laws of physics are supersymmetric, supersymmetric partners, squarks we call them, selectrons, photinos. This particle is a fermion with a spin of a half. This is a boson with spin 0. The photon is a boson with spin 1. The photino is a fermion with spin 1/2. Now, none of these particles have ever been seen. You might say, okay, beautiful theory, throw it out. Contradicts experiment. But wait a moment. We've learned that not all, well, we haven't learned. I didn't tell you that, well, we have learned that all symmetries of the laws of physics need not be symmetries of the vacuum. So, for example, let's go back to rotational invariance. The laws of physics are unchanged when I do rotations. But this room is not rotationally invariant. You're there. You can see all your faces. Now I rotate 90 degrees. I don't see anyone. Does that mean that rotational invariance is not a symmetry of nature? No. The laws of physics are still rotationally invariant. This room isn't. That's because you all came into this room and you sat there and not there. So take you all out. Take everything out of the room. The people, the chairs, the air. You're left with a vacuum. The vacuum is surely rotationally invariant. There's nothing there. But remember what the picture of the vacuum was. This complicated sloshing medium. It's not obviously rotational invariant. In fact, we've learned that there are many, many symmetries of nature that are not symmetries of the vacuum, that are not manifest in the vacuum. And in that case, even though the laws of physics are invariant under the rotations, their manifestation of that symmetry isn't so simple. And in particular, these new particles need not have the same mass as these particles. So supersymmetry could be, and in fact we now understand that it's very likely to be, broken in the vacuum. And if it's broken at the scale of 1 TeV or 100 GeV, trillion electron volts, then the superpartners would be heavy, and they would weigh this scale of masses. And this is the scale that the LHC can produce. So we have never seen these particles simply because we never had enough energy to see them. And now we're going to, so we will see them. Now you might say, okay, theorists are clever, you found a way out, but why? What's special about this number? Why do you expect to see them at the LHC? Why haven't you seen them before? Or why maybe it requires an even bigger accelerator, and you'll be coming and asking for more money. Well, there are many clues that pick out the region that the LHC is going to explore for supersymmetry to show up, for these superpartners to show up, and I'm just going to talk about two briefly. One is this unification of the forces I talked about. That beautiful picture where the forces came together doesn't work, really, in the standard model. This is inverse force on a logarithmic scale. Then you get straight lines. This is actually the strong force getting weaker. This is electromagnetism getting stronger. The three lines do not meet at a point. Three lines don't have to meet at a point. Well, what could this be telling us? It could be telling us the forces don't unify. Or it could be telling us that we're missing something. Well, if we make the standard model supersymmetric in the simplest possible way, and that's very easy to do, then something comes in, more particles that fluctuate in this vacuum and change how the forces behave. And now, remarkably enough, the forces do come together after extrapolating 14 orders of magnitude with 1% precision at this point where, again, gravity becomes strong. Well, that could be telling us the forces do unify. Nature is supersymmetric, and the scale of the new particles is a TeV, or it could be a coincidence. Well, some of us, like me, say, this clue is too good to give up. It's an indication that supersymmetry is there at a TeV. But, of course, it could be a coincidence. The other coincidence, or clue, is dark matter, which was discovered last century by astronomers who discovered a form of matter that exists in our galaxy and holds these stars in place. There's not enough visible matter, astronomers determined, just using Newton's laws. And they model the galaxy with a halo of dark matter. This discovery has been confirmed in many astronomical and cosmological ways by now, so it is just about accepted by everyone. One of the clinchers was this beautiful bullet cluster, which is supposed is a picture of two clusters of galaxies colliding. And the blue, well, this is another picture of it. The blue is the rendition of the measured density of dark matter, which has separated from the ordinary visible matter. The visible matter is visible in the X-rays. These are ionized clouds. The dark matter is visible because it bends light that comes from quasars behind it, and you can measure the density of the matter even though you can't see it by the bending of light that it causes. So astronomers have concluded that most of the matter, that most of the matter in the universe, 90% of the matter, not the energy, there's only about 30%, 27% of the total energy in the universe, but most of the matter, particles, is made out of, is so-called dark matter. And in modeling galaxies and the structure of galaxies and how galaxies and stars are formed, they conclude that the most likely stuff that this dark, non-visible matter is made out of is just a heavy kind of elementary particle. Heavy means 100 GeV or so, the mass of a heavy nucleus, that doesn't interact with our kind of matter except very, very weakly. Now, the astronomers have no way of saying what these particles are. That's the business of particle physics. Theorists said, okay, this is good because supersymmetric extensions of the standard model naturally produce such particles. In fact, a back-of-the-envelope calculation tells you that if the mass of these heavy particles, supersymmetric new particles, is about a TeV or so, then you can calculate or estimate how much dark matter there is out of all the matter in the universe, and it comes out to be in the right ballpark. That is another important clue or a coincidence. But we can test that, the Large Hadron Collider. We can, with this incredible machine that's only a few kilometers from here, which I hope you all have visited or will visit. It's shutting down, so you'll be able to go down and see the detectors in principle. They are incredible creations of modern technology and science. And in these detectors, we have a chance of both finding the predicted Higgs boson, confirming this picture of the weak force that we have, and I have no doubt that that will happen. But even more excitingly, and perhaps even earlier, of discovering supersymmetric particles. And this is a simulation of a typical SUSY event that one might see in the ATLAS detector. And the way one would see it would be, you see these jets of energetic particles going off in this direction and this direction. There's almost nothing going off down here. You add up the momentum and the energy, and something is missing. That could be the lightest supersymmetric particle, which would be stable, which would escape from the detector, not be seen. It would be a sign of supersymmetric lightest particle, a neutral, heavy, weakly interacting, exactly what one needs to describe dark matter. So not seen energy and momentum would be a sign of supersymmetry. I want you to remember when you read in the Swiss newspapers, which I'm sure will cover the press announcement, that scientists at CERN have claimed to have discovered supersymmetry, and they will claim that long before it is sure that it's supersymmetry, but that will come as well, that what they're really discovering are quantum dimensions of space and time. That it will be correct, this having been discovered, to conclude that we live in superspace. Space, after all, space-time that we're so familiar with, is one of the marvelous intellectual feats of an infant. To construct this description of reality based on touching and feeling and trying to move around. And now, after a few tens of thousands of years, with the help of the LHC, we'll realize that we're actually living in superspace with quantum dimensions. I'm going to end with a few remarks truly about the very, very large and the very, very small. And it all has to do with the universe, which once was very, very small and is now on its way to being very, very large. We know an immense amount about the universe. Over the last 100 years, astronomers, astrophysicists, cosmologists, particle physicists have learned just about a very good and quantitatively tested story about the history of the universe over 13.7 billion years. From the Big Bang, which we know nothing about, the beginning, a period of rapid accelerated expansion called inflation, and then settling down to a period of approximately constant expansion. Now, what happened during inflation was that a boson field, in our simplest pictures, a boson field was relaxing to its lowest energy state. And while it was relaxing, it was causing, because of the fact that matter and energy curve space, it was causing an accelerated, very rapid, inflationary growth of the universe. If that were just the case, the classical case, we would end up with a pretty boring universe, with all of its texture smoothed out by this rapid, rapid expansion. And nothing interesting would happen, and we certainly wouldn't be here. It is the quantum fluctuations of that bosonic field, we believe, that is responsible for the texture of the universe and for the fact that we're here. These are quantum fluctuations that grow and give rise to a slight clumping in the matter and energy density of the universe. And our best picture of this, and the reason this is based on observations of the universe as it looked 13.5 billion years ago, in the microwave, in the measurement of the microwave background. Here you see a pretty homogeneous bath of radiation and matter with very small fluctuations that have been magnified in this WMAP picture by a factor of 10,000. Were they not magnified, you would see no structure at all, complete homogeneity. These small fluctuations, according to the very quantitatively successful theory of inflation, arise from the quantum fluctuations of this bosonic field that drives the inflation. Now, eventually, these little clumps of extra dense matter and radiation pull, condense, contract because of gravity, and form stars and galaxies and the structure of the visible universe, extending out to 10 to the 26 meters. We believe that all of that structure, and cosmologists and astrophysicists claim to be able to reproduce the observed structure, starting with those quantum fluctuations that originated at 10 to the minus, 30 centimeters. So this is an amazing connection between the smallest possible scales of the universe and the largest. But it gets even better. What about the Big Bang itself? Well, when we extrapolate this very successful picture of the universe backward and backward in time, we end up with singularities, which really means everything breaks down. All our descriptions of gravity, even string theory, so far, hasn't helped us. There's no question that this Big Bang, what started out the universe, is completely quantum. In fact, exhibits quantum effects that we do not understand at all. There's a question mark here because we have no theory. We have no explanation. We don't even know what it would mean to have an explanation of the beginning of the universe. But quantum fluctuations, quantum effects are going to be dominant. And finally, let's go back to the vacuum. One thing that's been observed in the last few years is that the expansion of the universe is once again accelerating. Very little at the moment, but it'll get bigger. And that acceleration of the universe most likely is due to what Einstein called the cosmological constant, but should really be thought of as the vacuum energy. Now remember that picture of the vacuum full of fluctuating fields? Finally, I got it back. There's a lot of energy in the vacuum. Those fluctuations, like the pendulum, have this zero-point energy. We've never found a reason why it shouldn't be there, and it's finally been measured. We don't understand why it's so small, but it's very natural. In relativity and in general relativity, in quantum mechanics, the vacuum has these fluctuating fields. We see their effects, and they carry energy. And that energy will act on the geometry. Matter curves space. And in fact, it causes that vacuum energy an accelerated expansion of the universe. So these quantum fluctuations in the vacuum give rise on a cosmological scale to an accelerated puffing of the universe, expansion. And that will dominate the universe in the future. In the future, 10 billion years, or maybe 100 billion years, I forget, from now, if you were to go out, maybe not in Geneva because it's hard to see the stars, but on top of the mountains and look at the stars, you'd only see our galaxy, the Milky Way, and maybe some other galaxies that are gravitationally bound to us. All the other 10 to 100 billion galaxies in the universe would be moving away from us with speeds greater than the velocity of light because of this expansion. And we would not be able to see them. The sky would be very black. We'd be in a very lonely part, all by ourselves in our cluster of galaxies. So the teeny quantum fluctuations of the vacuum might very well dominate the final history of the universe, connecting the very, very small to the very, very large, the very, very early to the very, very late. So to end, what is my message and the message of all my colleagues? Quantum mechanics is the framework for describing all these wonders of nature that we're in the business of exploring. And from the very, very small to the very, very large, and everything in between. Thank you.
Okay, we'll have in a couple of minutes, we'll start the roundtable discussion to answer questions. Il doit y avoir des petites pièces de papier. Mais je ne les ai pas vus. Ils sont où les hôtesses? Bon, maintenant, à part la roundtable discussion, vous pouvez aussi poser des questions dans des petites pièces de papier que les hôtesses amèneront aux conférenciers. So let me repeat it again. There will be there are some pieces of paper where you can write questions that will be brought down for the speakers to answer. And those that will not be answered during the discussion will appear, or their answers will appear in the web page of the conference. We'll try to answer them anyway.
I was wondering how you would and I think his negotiation must have effect, and I don't know, but it gave an impression.
You can buy super silver.
The Spanish club, le club espagnol, est drôlement vivant. Avec des pesetas. Je dois en avoir quelques-unes encore à la maison. Alors, quelques pesetas. Je vais vous porter quelques pesetas. Oui. Oui. Oh, mais ça, c'est lui qui va dire ça. Pas vraiment de ça, mais bon. Merci. Einstein forever. Einstein on the beach.
Okay. You can start. This microphone doesn't seem to work very well.
Let's go.
I suppose we will not have much to say.
Very inspiring.
I
Merci.
expect that we are going to be very
C'est pour
quiet.
nous très bien, oui.
Oh, yeah,
Ah, mais c'est
rewriting
pas pour les
it
gens qui ne
for
comprennent pas.
Rainer, there's a
Peut-être mon
question
accent.
for you.
But
Does dark matter lead to decoherence of a quantum computer?
our friends will have.
Okay, maybe we can start with the first question.
That's their problem.
Now, I think that this could go to Professor Cross or to anyone else who wants to take the question. If the galaxies go faster than the speed of light, is there a shock wave, some kind of luminous shock wave as that for the speed of sound or the,
Now, they're not going. You know, we actually observe in our I don't know whether it's in our galaxy, jets coming out of probably black holes in opposite directions with a relative velocity between them, which is bigger than the speed of light. Each jet is moving with velocities less than the speed of light, but this is in opposite directions. And so this does not contradict Einstein's theory, and there's really no problem. What is accelerating here is truly the fabric of space itself. And that's taking everything with it that lives in space.
One more question. Let's see. Is the mass of the universe increasing with expansion?
Well, is the perhaps better to say whether the energy of the universe is increasing. Energy in Einsteinian relativity is not such a simple concept. In fact, if the universe were closed and we're not totally sure that it isn't, the energy of the universe is, the total energy of the universe is always zero. The expansion of the universe would seem to cost energy, but you can get that energy from, if you want potential energy of gravity, easily. The easiest analog is one we're quite familiar with. If you have a planet which is moving around the sun like the Earth, and if it falls in towards the sun and gets closer, it speeds up. Where does that energy come from? Well, it comes from the potential energy of the gravitational field. The same is true of the universe. In fact, in inflationary, Andre Linde, one of the inventors of inflationary theory, once said that inflation, which is an enormous expansion of the universe, is a free lunch.
Well, there is one question here which is kind of interesting, probably dedicated to all the others, so that Professor Gross can have some rest. Is, what does the picture, the colloquium poster, represent? Do you have a picture? Please. You want to answer?
I can answer this one. It's a trick question. It's a representation of the cloud of the electron around an hydrogen atom. And we'll put the detailed explanation on the website of the colloquium. But it's essentially an hydrogen atom.
Okay, one more question. Will CERN or the LHC be powerful enough to test unification?
Unification happened 14 orders of magnitude higher in energy, we believe. So not clearly directly. But indirectly, maybe, if we're lucky, certain aspects of ideas or speculations about unification could be tested. For example, if all the forces unify, the same should be true of the nature of the particles. They should look the same in some way at very high energies or short distances. And in fact, they fit together in a very nice way so that that could happen. But specific models or theories of unification predict that you could follow their masses, which also, because of the dynamics of the vacuum, change with distance scale to the unification scale, and they should also merge in a predictable way. So by doing experiments especially on supersymmetry, we might learn, if that turns out to be the case, we might get many, many new hints about the unification, about the specific dynamics of unification, the same way we got from the running of the couplings. But all of these are indirect and not as good by any measure as direct experiments. But, you know, we can't build a collider at the Planck energy, and we're not going to be able to in the foreseeable future, if ever. So we have to do what we can. We hope to get as many clues to improve, disprove some of our speculations.
Well, this is a very challenging question. If a tiny fluctuation can generate a whole universe, how the principle of energy conservation can be satisfied?
As I said, energy is a tricky concept in general relativity. The vacuum energy is a very strange form of energy in many ways. One way, by the way, is you cannot tap it. You can't use it. You can barely detect it. 70% of the energy of the universe is in this vacuum energy, according to observation, and it is almost impossible to detect its existence except by measuring this acceleration of the universe, which is not easy to measure. Now, why is that? Well, one simple explanation is that a vacuum filled with vacuum fluctuations that produces a vacuum energy density, and by the way, a pressure density, is not an ether. Somebody could have asked, if you're filling the vacuum with all this stuff which carries energy, why isn't that the ether? And indeed, if the universe was filled with ordinary particles which produce energy, a gas that has energy and pressure, that would be an ether and would pick out a distinguished frame, a distinguished observer. You know, because, for example, I have energy, but if I'm running, I have more energy. So there's a particular frame where I'm at rest. The vacuum energy and pressure, the pressure and energy of the vacuum is the only kind of energy and pressure that doesn't define an ether, that looks the same to all observers. That's why it occurs naturally in Einstein's theory, and why it's the default explanation of the acceleration of the universe, and why the test of that particular kind of funny energy and pressure is in my opinion, a marvelous 10% verification of Einstein's ideas. And by the way, why is the universe accelerating? That's sort of anti-gravity. energy pulls it, makes it contract. And that's correct. The vacuum energy actually causes the universe to contract. The reason the universe is actually accelerating is not because of dark energy. It's because of dark pressure. That stuff in the vacuum has energy, like a gas, and it has pressure. But the pressure, in order for it not to look like the ether, has to be negative. So it's the negative pressure of the vacuum fluctuations that causes this sort of anti-gravity or the expansion of the universe. And it's only that very strange kind of negative pressure and positive energy that doesn't act like an ether and define a preferred state of reference.
Okay, one more question that perhaps somebody else could answer. You know, be bold. Do you have any imagination or any way of describing what could there be before the Big Bang?
No.
That's a tough one. That's a tough one. Especially before dinner. Please, David.
People, you know, when I was a graduate student and you wrote a paper that addressed that question, you couldn't get it published in a respectable physics journal. Today you can. That's progress. It means that we can start thinking about these questions in a truly scientific fashion, and there are people who have all sorts of ideas. There are people like Hawking and my colleague Hartle who believe that the universe sort of wasn't anything like in existence before it came into existence, and it came into existence via a quantum tunneling event. It tunneled out of something else. Something else is sort of a space-time without time, and so there's no meaning to what happened before. Now that's bizarre. There are people who speculate that the universe before the Big Bang was a universe that was contracting. The universe is cyclic, that it contracts and expands and contracts and expands forever. And then there are people like me who don't think we have the concepts yet to answer the question. And that a question like what happened before time began might be answered by changing, as often the case in physics, by modifying our concepts so that we realize later that we asked the question in the wrong way. That's what I believe.
Sorry, this question I think is addressed to you. Obviously, anybody else can take. Some people claim that string theory does not satisfy the criterion of falsifiability. Could you comment on this?
Well, string theory isn't yet a theory. In fact, 26 years ago when we came up with a heterotic string, which looked like it had all the elements to reproduce the standard model, and even though we could only make predictions at that time at what would happen at the Planck length, we believed that within months, years, we could calculate properties of the standard model which we're still unable to calculate. That's one way of verifying theories, by solving theoretical problems and postdicting numbers that are well measured. But by now, I think I'm convinced at least that we don't yet have a theory. We have a framework. The framework continues to astonish us with its power, hasn't lost any of its previous power, but also not its lack of predictability. It is less revolutionary than we first thought it was, and it's by now essentially impossible to kill. Not because we can't test it, but because it is connected in a almost continuous fashion to theories which are extremely well tested, the Standard Model. In fact, we believe, and we're making enormous progress on formulating quantum chromodynamics and the properties of hadrons, those flux tubes which look like fat strings, in terms of a string theory formulation. We now understand that string theory isn't really different than quantum field theory. It's just another part of the bigger framework. But it's still a framework with something missing that picks out a particular theory. And therefore, it's not yet falsifiable or predictable, just as quantum field theory is very hard to falsify. What is possible to falsify is specific quantum field theories like QCD, which makes predictions. String theory is more of a framework, and it's a framework which contains within it, it appears, everything we knew about quantum field theory. So you can't kill string theory without killing the Standard Model, which is unlikely.
Very good. Okay, one more question. I'll try to paraphrase it a little. I never understood how the inflation phase or the inflationary phase of the universe could happen at speeds greater than light. Similarly, 100 billion years from now, it seems that the galaxies will be running away from us faster than light. Isn't that in contradiction with special relativity?
They will be if the accelerated expansion continues. And no, it's not a contradiction with special relativity. There's no causal connection between these galaxies that are receding with speeds greater than the speed of light. And as I said, we can see this happening in the visible universe. There's no contradiction. Indeed, the expansion, this accelerated expansion, caused parts of the universe to indeed be causally disconnected, moving greater than the speed of light with respect to each other for quite some time. And as we look farther and farther out in the universe to fainter and fainter regions, we're seeing stars that are just now able to communicate with us. So when you look at very far away stars, 13 billion light, or, well, I don't know whether we could look that far, 12 billion light years out, those galaxies and stars weren't able to communicate with us until quite recently. They've slowed down compared to us. Eventually, because of the expansion of space-time itself, the accelerated expansion of space-time, we will lose contact with them again.
Well, this is a very nice philosophical question, which is a quotation from Leibniz. Why is there something rather than nothing? Where does the vacuum energy come from?
So when people ask that question, sometimes I give these talks and I seem to have an answer for everything, and so they want to get me and they say, why is there something rather than nothing? I say, that's not a scientific question. There are questions, fascinating questions that we are facing, which we can approach by observation or by experiment or quantitative reasoning, speculation, theoretical reasoning. But why is there something rather than nothing? It's a question people, even I, ask myself once in a while. But it's not that interesting, because you cannot approach that question by observation, by experiment, by rational thought, and quantitative modeling, quantitative speculation that could be related to observation or experimentation. So I don't find such questions interesting, and they're not scientific questions, therefore.
Maybe the last one. Is there a place that could be identified with the location of the Big Bang? Does it make
That's
sense?
another misconception. The expanding universe is not an explosion. The Big Bang is not a piece of dynamite that explodes. It's more like a balloon. The simplest analogy is a two-dimensional world, which has the topology of a sphere. And the galaxies are little blotches on the sphere. And the acceleration of the universe is like blowing up the balloon. If you're sitting on the balloon at any point, you look around you, you see all the other points, the blobs are moving away from you. And the ones that are farther away from you are moving faster. That's what we see. And any other point on the balloon would see the same thing. And one of the well-tested principles of cosmology is that every point in the universe sees the same thing. So we're not the center of the explosion, and the explosion didn't happen someplace in the universe. The whole universe is puffing up. The distances between all points, just like on the balloon, are expanding at a constant rate, at an accelerated rate, but the whole thing is expanding.
It happened everywhere and everywhere. Okay, I think it's a good moment to stop, otherwise Professor Brosh will lose his voice.